Planck Institute, and she's going to tell us about axionic wormholes.
So, hi everyone, and thanks for being here. So, I'd like to present this piece of work I've been doing with my PhD advisor, Jean-Luc Lénas, and a collaborator, Georges Davalashvili. And it's about solutions we found in an axion gravity theory, so Euclidean wormhole solutions. So, first, let me tell you what Euclidean wormholes are. So, basically, Euclidean wormholes are solutions that appear when we consider the Euclidean path integral approach to quantum gravity. And basically, these are solutions that represent a topology change. And so the basic question is whether topology change are allowed or not in quantum gravity. So if they are allowed, then we expect these Euclidean wormholes to play a role in the path integral, but then this comes with many puzzles that I will describe. And if they are not allowed, then we have to explain why this is the case, because we know that, for example, in two-dimension topology change should be allowed. So this is on the right, you can see a semi-wormhole, and you see that it describes the topology change from this sigma 1 into this sigma 2 cross sigma 3. So if you look at this kind of solutions in general relativity, you don't find any. And the first such solution were found by Giddings and Strominger in 1983 in an axion gravity theory. And so from the time that these explicit wormhole solutions were found, all the puzzles that come with them were made more were really becoming relevant. So just to name a few of these puzzles, you have an apparent non-unitarity when you have these wormholes, but if you try to solve this apparent non-unitarity, you get random values for all your coupling constants. You also have problems in ADS-CFT related to ADS non-locality. And then when you try to, there is the big question of whether these Euclidean wormhole solutions are really stable solution or not, or if they exhibit negative modes. There are many other interesting phenomenological and theoretical implications of Euclidean wormholes. If you want to learn more about it, I really suggest reading this review by Arthur Ebecker and collaborators from 2018. So now in this talk, I will present to you new solutions we found when studying axion dilaton gravity theories where the dilaton becomes massive. And this is believed to be of interest because we usually if you take this kind of theory coming from string theory, you expect the dilaton to have a mass. So just to remind you or maybe tell you what the Giddings-Strominger wormhole solution are, so the basic solution found in 1983. So here you have the Euclidean action that has a Ricci scalar term, and then the kinetic and potential terms for the dilaton. And then you have the tree form of the axion that is coupled to the dilaton with the dilaton coupling beta. And so this diagram shows it's an embedding diagram showing representing this solution. So you have the throat and then the asymptotically flat space, and you can imagine that the Euclidean time is running up in this diagram. And so for finding this specific solution, we have to look at a spherically symmetric and homogeneous ansatz. And by doing this, we find that for null potential, there is always a solution where the dilaton coupling is smaller than a certain value that we call the critical beta value, and it's about 1.63. So now the question is, how can we generalize this kind of solution? So this is an analytical solution, and now we want to generalize to the case where the potential is not zero, but actually has a massive term. So if we do this very generically, so we assume the same initial conditions. So we put initial condition at the throat such that the scale factor is scalar field at 0. And then asymptotically, we want to recover flat spacetime. And then by doing this, we find that there is actually a necessary condition of existence of this wormhole solution, which is written here and which depends on the potential. And when this solution is satisfied for the potential, there is actually always, so there are two solutions for the scale factor, for the initial scale factor. One corresponding to what we call contracting baby universe. So these are the usual Giddings-Ströminger's wormholes, which leads to a contracting baby universe when you analytically continue to Lorentzian spacetime. And then there are these new other solutions that lead to expanding baby universe when you analytically continue at the throat. So we are going to study these two solutions. And so first, let me show you what we find for the massive case of these, for the contracting solution. So these were already studied before, but here we found more solutions, new branches of solutions, and we also found the appearance of what we call oscillating solutions. So these are solutions where the scale factor, before reaching the asymptotically flat spacetime, it will oscillate somehow. And so this, for example, is what we find for one set of parameters, and you see that we don't find only one wormhole solution, we find many. In fact, here, for example, I plotted 5 solutions with 1 minimum, and then one solution that is only that has 2 minimum, which is this gray solution. And so what is very, very weird about these solutions is that the Euclidean action is actually smaller for the solution that has more minima. So this is very counterintuitive, because it means that in the path integral, the solution with 2 minima will have more a bigger weight in the path integral. So this is somehow intriguing, and we can actually look at what the family of solution looks like. So for instance, here you see, I'll start with the bottom. So you see the brown line. This is what was found previously. So these are solutions that are related to the mass zero wormhole solutions. And here we found that in addition, we have another branch of solution that continues into oscillating solutions. So the dashed lines correspond to oscillating solution, and you can really imagine that they continue zigzagging for higher values of phi 0. And then what is very interesting is that we observe there is this bifurcating branch phenomenon appearing when the beta value grows. So you see between the purple and rose pink line, there is this shift that the branching solution goes from the 2 above branches to the one below. And this actually explains why in the mass equals 0 case, we only, so after some point in the mass 0 equals 0 case, after beta critical, there are no more solutions. And now we understand that actually what happens is that this above branch just vanishes, and then we only keep the bifurcating branch below, like this, the one for 1.64, you see. So this is very intriguing, because there is much more features and much more going on that was previously thought. And so this, for example, so this is the full solution, but so basically I just gave you the main features before, but so we did this for a large range of beta values. And so this is for the contracting baby universe case, and now for expanding baby universe. So just to give you an idea of what the expanding baby universe solution look like, so you see that the scale factor first goes down before reaching the asymptotically flat space. And similarly, we studied the structure in branches of this solution, and we also found bifurcating behavior. But in this case, we don't have a branch that connects to m equals 0, because analytically there is no solution at m equals 0 that are expanding. And so here we recover the same weird feature, that the action, the Euclidean action, gets smaller when you have more feature of your solution. So when you get several oscillations, for example, your Euclidean action gets smaller. So yeah, that's what I wanted to present to you today. So just a few last comments. So I've shown you that we can find many solutions when studying this axion gravity coupled to a massive dilaton. and we can find both wormhole solution that leads to an contracting, so giving Strominger-like wormhole solutions, or expanding baby universe. And so we also found these very counterintuitive results, that solutions that have more feature have a smaller Euclidean action. And so I didn't have time to present this to you, but we also studied another potential, which is a potential where you don't have the Dieladron coupling is set to 0, but we get double well potential. And in this case, we also find contracting baby universe. And there, it was quite different, because the action was instead better behave in the sense that when you get more oscillation, the action was becoming bigger. So it means that it will will be suppressed in the path integral. But we found some negative Euclidean action for some wormholes, which is also very puzzling. So finally, for some outlooks on this work, it would be very interesting to look at the stability analysis of these solutions. So this has already been done for axion gravity theories, but not with a massive dilaton. So in particular, what must be included is the study of the stability for the dilaton and scalar field fluctuations. And then what would be, of course, very interesting is to understand what is the meaning of this bifurcating behavior, and whether this tells us something about the physical relevance of these wormhole solutions. And so just to mention that this kind of Euclidean wormhole solution, we looked at them in the with an asymptotically flat space, but you can also look at asymptotically de Sitter space. So this was done recently by Ertok and collaborator, and you could do the same with ADS, and in order to, for example, tackle the problem of ADS non-locality. So thank you very much for your attention, and I'm happy to welcome any question.
Yep.
So, if these topology change, if these topology changing spacetimes are allowed in the path integral, what does that tell us about topology change in like some semi-classical limits? Because what I know is that if you put matter fields on topology changing backgrounds, you get into problems with global. No, it's not on. Well, But I believe, I hope most people heard what I said. If not, yeah. So basically, if topology change is allowed, will that also lead to topology change at macroscopic scales? And how is that? Can that be?
Mm-hmm. So
can that be made sense of in any way?
Okay, so I guess that this is completely tied with the fact that there are so many puzzles that arise when you consider topology change, because they are really not only that these are quantum effects that are not only relevant at the microscopic scale, but also at the macroscopic one. And I guess this is precisely why this question is so interesting. And to be honest, we don't have an answer of whether this is allowed or not. But in the idea of quantizing space-time, it's something that is pretty natural to assume that fluctuations of space-time would also include fluctuations of topology. But indeed, it's a problem for macroscopically.
Because I think De Wit has argued that topology change should not be allowed because you cannot put a quantum field on that background, essentially.
Well, for example, in the 2-dimension, you can change. So, for example, one can do quantum field theory in 2-dimension with topology change, right?
But there won't exist. But you won't have a global existence of Hadamard state.
Yeah. So, of course, you need to change how you define precisely all your mathematical structure. But I think that, for example, in 2-dimension, this has been done. So
well, you can define it as an algebra of observables, but if you actually see how the expectation values propagate, you see that things will diverge. But
okay.
Maybe there is new work that I'm not familiar with.
It's I mean, it's mostly pretty standard work, I would say. Yeah. Yeah. Maybe this. Yeah. I don't know.
Well, perhaps
maybe
we can discuss it in
this,
person.
yeah.
Yeah.
Let's thank our speaker again.